Thank you very much. It's an honor to be part of this conference, not in the least because the company of the speaker is just amazing, the audience, but I'm also super happy that I speak on the day honoring Norbert, because when we arrived in Montreal, it was Norbert and Dana who made the most welcoming and warm committee. Yes, François, I know you too, but, but after Norbert and Dana. And it was just something that at the time we didn't maybe appreciate enough. And it was also that we did not know what pillars of the mathematical community they were in Montreal until a few months later. So at the time when I met Norbert, he was very interested in the man behind the mathematician. And I say man, not to say person, but it's really because there is a depth to that interested him in the sense of what toll the creative process takes, what is the level of confidence or not, or what is the humbleness of a person or not, whether a good mathematician or not. And I think that there were many comments in the conference about how he put mathematicians in two categories, and I think most of it is due to the man behind the mathematician, not the mathematician. Included in this, it's also the political view of the people. So it was a lot of qualities or traits that he looked at, and I believe this happened in the later part of his life. I can't say for sure, but it really impressed me, and I think that for people close to him, it was always unconditional support and positivity. So in this regard, it wasn't really any kind of criticism or any kind of reservation. He was there fully for one close person. Okay, so since the initial day of the conference in January until now, two things have passed. One was, and I don't know if this was a coincidence or not, but the day of the conference is a day after Norbert's anniversary of his birthday, if I'm not mistaken.
It is the very day of his 90th birthday anniversary.
Today. Okay, so I thought it was yesterday, and I thought maybe that was made on purpose, and maybe it was. And that's very nice. It cannot be more fitting. And then I also changed a little bit my talk. So if you did not read the abstract, it's better, because I decided to go for a more formal colloquium talk in geometric analysis, which is not quite integral convex geometry, but it's close, and it uses a lot of the convexity. So I may come back at the end and say a few words about Norbert, but it's really an honor and a moment of joy for me to talk at this conference. So the talk is meant to be a colloquium type talk, but to bring in some results of my own with a group of collaborators that spread over a few papers. And let's start. It's an eigenvalue problem, and let's start with an incredibly trivial fact that if you seek a function and a real number on some function on some interval 0d, and you look at this boundary value problem, this Levin problem, you immediately see that the boundary condition can be realized if and only if lambda 1 and that all the lambdas are positive, and they have to do with some multiples of the reciprocal of this word. So it's extremely simple to see that the first eigenvalues of this problem have a difference of 3 pi squared over d squared, where d is the length of the interval, and this is independent of the interval. In fact, you can translate it, and the problem is translation invariant. The difference between the two eigenvalues remains the same, depending only on the length of the interval. And now, so keep this in mind, because now I want to talk about the eigenvalues of the Dirichlet Laplacian. So we have the Laplacian on Rn, and we impose on some domain, doesn't have to be convex, compact domain in Rn, and we look at the eigenvalue problem so that we have the Dirichlet boundary condition. And then because the domain we take, it's compact, immediately we see that the spectrum is discrete and the first eigenvalue is simple. And so it makes sense again to look at the difference between lambda2 and lambda1 because it's not zero. And then that by definition is called the fundamental gap. So the fundamental gap is the object of my talk today. Some bounds on it, lower and upper bounds, somewhere well known. And it's a little bit of a history of the problem, and it's very interesting for this, at least for me, for this end of the day. And this is not restricted to Rn. This is a problem that could be formulated for any domain that's on a Riemannian manifold. And you just have to take the Laplace-Beltrami operator, but no fear. It's really in the typical cases of this talk will be only Rn, Sn, and Hn, the hyperbolic space. But the problem is the same. We're looking at the eigenvalues of the Dirichlet Laplacian, and the spectrum is discrete and diverges to infinity, and we're looking at the first two eigenvalues, which have a difference strictly positive, and this happens even if we modify the operator from the Laplace, the negative Laplace operator, to the negative Laplace operator plus a potential function, which is positive, and we'll see later that there are some results related to this. This will be the Schrodinger operator, and it's related. The problems are very much intertwined. Okay, so let's talk a little bit about the bounds on this fundamental gap. So the first one is the upper bound, and it has the feeling of an isoperimetric inequality. Because really what we want here is we fix a normalization. We fix that the lambda1 of the first eigenvalue of the domain is the same as the first eigenvalue of some ball of a certain radius, because they go from 0 to infinity. And so then we look at the fundamental gap of the domain omega with the same eigenvalue as that of a ball, of a certain ball. And we realize that the fundamental gap is upper bounded by the fundamental gap of the ball. Okay, so it is like an isoperimetric inequality, because if you're thinking about the classical isoperimetric inequality, which is surface area at a certain power divided by volume, it's minimized by the balls, right? So this is maximized by the balls, but it has the same flavor. And in fact, the proof goes through some kind of symmetrization, which is very similar with the classical isoperimetric problem. And this was at first known as a conjecture, Payne-Polya-Weinberger conjecture, and it was solved in different spaces of constant sectional curvature, not only in Rn, but also on the sphere, where we had to limit ourselves to the upper hemisphere, and then in the general case, then in the hyperbolic case a bit later, sometime later. What I want to add here is that the convexity is not needed. Okay, because I'll come back in a moment at the lower bound, and in that case of the lower bound, we'll see that we'll add the convexity condition. So here the domain is just a compact domain, and that's it. And let's go a little bit over just an idea of the proof, because it has some elements that I'll need a little bit later in my talk. So it's known by well, actually, you may know about Lord Rayleigh, who was actually studying wave equations and other problems in physics. That he found variational definitions of eigenvalues. So those quotients are called the Rayleigh quotients, and you can describe each eigenvalue of most of the operators, in fact, as a minimum of some ratio, which is the L2 norm of the gradient of a function over the L2 norm of the function. The catch is that if you move from the first eigenvalue to the next one, you have to keep, since you're minimizing over a set of functions, a class of functions, you have to keep away from the functions that already gave you the minimum from lambda I. So when you go to the next space, to the next eigenvalue, you have to look at the space that's orthogonal to a complement of the space in which your eigenfunction of order I lies, so you can get to the next one. And so this is really very helpful when you're trying to prove upper bounds, because the actual calculations of eigenfunctions and eigenvalues is pretty hard unless you know the domains are very special, balls or parallelepipeds and so on, where you can do some classical techniques, separation of variables and so on. but otherwise it's very, very hard. But what you can do though, is that you can look at the first eigenfunction, which you may or may not have exactly, and then because you want to upper bound or upper estimate the difference lambda 2 minus lambda 1, take a good test function for the Rayleigh quotient that's realizing lambda 2, because if all you have to do is find the function that's orthogonal on U1, which might be abstractly done, and then that function, which is a good test function, gives you a slightly larger, maybe a slightly larger value of the Rayleigh quotient than lambda 2 is, but you are able to find an upper bound this way. Okay, so the idea was here for the proof of the Payne-Polyak-Weinberger conjecture that you take V1, which is the first eigenfunction of the problem, which is the Laplace operator, the Dirichlet Laplace operator eigenvalue problem, and then you modify, you choose a very well thought of function P, such that P times V1 becomes orthogonal to V2. That's the condition integral bv1 squared dx equals 0, and you use that function to compare the two Rayleigh quotients and get the upper bound together with some work on symmetrization to show that it's the bond. Okay, so that's a classical technique in the eigenvalues in spectral theory to use the Rayleigh quotient. And now, what about the lower bound? So this is the main object of my talk. So the lower bound has been a conjecture for many years, let's say. Appeared first in physics due to Vandenberg, and then also from the geometric and analytic point of view, Yau and Aschbaum-Benguia. And in fact, it says that the fundamental gap of any convex domain, this time convex in the sense of geodesic convexity, okay? So like any 2 points in the domain are joined by a geodesic, which is contained in the domain, so geodesic segment. So for any domain that's convex, and any V, I can even add, as I said, the potential function V, the fundamental gap is lower bounded by this 3 pi squared over d squared, which is the thing that I showed you in the beginning with the interval. That was exactly the same value of the Liouville problem in 1 dimension on the interval 0. And lower bound was conjectured to be approached when the potential is 0 and when the domain degenerates to a needle. So basically, degenerates to that segment that we were talking about on the first slide. And okay, so that was the fundamental gap conjecture, and progress was slow even in the one-dimensional case. If you can believe, the one-dimensional case was the one I had on the first slide, but without the potential. The moment you add the potential function, which was even convex, a convex function, it became non-trivial, and it was actually a professor at University of Rochester when we were their students, Rick Levine, who actually did it. At the time, I was not aware of it. I was not looking at the problem at all. I was not working with him, but it turns out to be a big deal that was solved. And then later there were progresses in all dimensions, but this is for Rn first. So Zinger, Wang, Yau, and Yau showed using a very neat gradient method, some bound, that was later improved by one of Yau's students and other people, 2 pi squared over d squared. So remember, the conjecture is it's 3 pi squared over d squared, and then oh, I want to note this because this is very interesting. The pi squared over d squared, and in fact, any bound was proved by exploiting the fact that the first eigenfunction of the domain, of any convex domain, is log concave. Okay, log concave is a function whose logarithm is concave. And what is the big deal about log concave function is the following, that like, for example, the density of the Gaussian is log concave. It's e2 minus a norm of x squared, or e2 minus x squared. So the thing is that it's quasi concave, which means that all the super level sets are convex. And so you cannot have two maxima of those functions. Those functions have like a unique maxima. They go, but they might not be balls like that. They might be like going smoothly toward the boundary and be zero at the boundary. So that's the key argument, was to show how log concave is the first eigenvalue. And okay, so the further estimates were obtained, but the final, also you notice that the years 2085, 86, and then 2003, and then it was finally proved not that long ago in 2011 with a very different method, kind of, in the sense of employing parabolic methods, so flows, curvature flows. I won't get into it, but and then after that, people realized how to bypass this and give proofs that were typically to elliptic equation and not necessarily going to parabolic equations. So the idea here was to study how log concave is the first eigenfunction. I'm giving some kind of measure of log concavity. And okay, so once this was done in Rn, people started to replicate this in the, or not replicate, but to really ask, okay, so the PW conjecture was true in all spaces of constant sectional curvature. So is this true in every space of constant sectional curvature? So normally you move from from Rn to the sphere, and then it was shown on the sphere to be true for any domains that were convex. So they're restricted to the upper hemisphere first, and then was natural to ask, okay, so we did it for, mathematicians did it for Sn and Rn, so why not to Hn, right? So why convex domains in Hn? And so, okay, so let me just go back for a minute on the log concavity. So how it was log concavity used really is you have U1 as log concave, and you look at the second eigenfunction, and you look at the ratio U2 over U1, which is well defined because U1 is strictly positive inside the domain. And then you look at the equation satisfied by that, and the log concavity helps you to find a comparison with a type like a standard model. A model is given by the one-dimensional model, so it's really super simple in both the spherical case and the Euclidean case. And the model exists in the hyperbolic, but the comparison is not there. That's what's missing. Is the comparison with the one-dimensional model that was not in the hyperbolic space. And in fact, so let me go back here. The fact just log concavity gives you a lower bound already, pi square over d squared, not the optimal one, but you already have a good enough lower bound. But the thing is that in Hn, what one could not show, in fact, there was a counterexample of a domain in Hn, in H2, in fact, for which the eigenfunction was not log concave. So we started, with a group of people, we started to look at this domain, the domain that had a not log concave eigenfunction. And it was not this domain for which we found that the fundamental gap is lower than the conjecture value, but it was the starting point. So let me say a little bit about this story. Okay, so the first result I want to say, but I don't want to take a lot of time on it, is that there are convex domains in H2 for which you get below the conjecture bound. And the way we did it was we took the Poincaré half-plane model, but we changed the polar coordinates, which are not very kind of, I don't know how to say, appropriate in a way, because they're not geodesic coordinates. Yeah, I mean the round circles, yes, but with orthogonal to the boundary, but the rays from the origin are not geodesic. So why did we do it? Is because, as I said in the beginning, it's very hard to actually have examples where you can of domains where you can hand-on calculate the first eigenfunction. So if you can use a separation of variable of sorts, you're onto something, and this is what we accomplished with that. The models we are looking at look like that. So they look like sectors. In polar coordinates, they are rectangles. So we can use separation of variables, and we have a form of the Laplacian in a hyperbolic in terms of the polar coordinates. So then we looked at the two eigenvalues via this way. So as I said, I don't want to spend a lot of time on this, but this is the example that started, the example that was given for some parameters of these domains, because you see there are lots of parameters. There are the angles of opening of the sector, as well as the height on the y axis. So the C gives you the height, and you have theta 0 and theta 1. So depending on such on such parameters, she has shown, and this is just to give you an idea, she has shown that you have some opening, some domain for which the first eigenfunction is not log concave. This was done through a variational argument, and actually was shown, he's shown that you can find a function that's an eigenfunction, and there are two critical points, and they have to be maxima. So that was contradicting the log concavities. And so we played a little bit with this domain, but in fact, this domain still had a lower bound, even if the first eigenfunction was not log concave. However, we managed playing, I mean, so this is technical, but what I mean to say with this is that you can actually look at this ratio or quantity that you kind of want estimated, and you can put it sandwich it between some expressions in terms of the parameters depending on the domain, and then actually if you play a little bit more with those bounds, you find some domain for which this difference, this fundamental gap is smaller than the conjecture one. Okay, so it's not the one that necessarily the one that she had, but was the same idea, was to play with this kind of domains and see what happens. And then we said, okay, so the fact that the first eigenfunction was not log concave was not really an impediment toward having a lower bound. So maybe there is just some lower bound we just couldn't figure out what. And so we continue along this way, and then we realize that no, in fact, for any convex domain of any diameter whatsoever, you can always find epsilon. So you can always find that. So for any d, you can find some domain of the diameter d. And for any epsilon given, you can get these two eigenvalues as close as possible. We call this like, there is no social distancing in the hyperbolic space, right? And I talked about it, so a couple of you heard this talk before in this direction. And so, okay, so there is no upper bound estimate on convex sets in HN. Let me just give you the idea why, because this is really heuristically, it's extremely interesting. We played again with the same type of domain. We realized that it's not important, it's not symmetric, and so we kind of rehash a little bit this. But look again at the domain. So it's just, we made it a little bit thinner just to get some. In the beginning, we thought that maybe the diameter is realized along the diagonals are P or SQ. Okay, that's easy to see, the diameter of this domain. So even if we make the length very like the thinness or UT very small, the diameter is still, it's almost like doesn't change that much. So we saw that maybe if we make this thinness very small, we're gonna get a counterexample. But in fact, what really is let's move from this model to the hyperbolic model. Okay, so that's the same domain in the hyperbolic model, the one on the left. Okay, so the QP, the QR and the PS are geodesics, but QP and RS are not. That's why they're a little bounded about, but the domain is still geodesically convex. Okay? It's just that the boundary is not geodesic. And if you think about this domain, the more you push the QP and RS toward the boundary, you realize you have more mass here. The distance is QP and RS, they move toward infinity, right? Because you're approaching the boundary, but the thinness, the waist of the domain, it's really tiny. You can make it very tiny. So that means if you look at the first eigenfunction, you might be able to construct an eigenfunction that has a lot of mass on these two parts, but has very little mass. It's a U1 is positive, but it's very close to zero around the waist, but very kind of big around here. So it's not going to be log concave for sure, but also let's see what it means. So the analogy we made between the domain, that domain was with the domain in R2. So everything here is explained in H2, but it works for HN. It's simpler to explain in 2 dimensions. We compared the domain with the dumbbell shape in R2. Why? Because, okay, so remember that convex domains in R2 have a lower bound, but non-convex, they don't actually. And so if you look at this domain, you can think about a first eigenfunction that's like the first eigenfunction of the ball here. just a ball by itself. Union, you define on that other ball the same eigenfunction. So you have two eigenfunctions of the sphere, and you tie them up here somewhat smoothly, so you can get a first eigenfunction for the dumbbell in R2. But then when you look at U2, when you look at the second eigenfunction on the dumbbell, remember you have to look among the class of functions that orthogonal on the first one. But my first function is so symmetric, it's like just a couple of balls, like upside down balls like that. So just take an odd function. Take a function that's like the first U1 on one ball and the negative of U1 on the other ball, and just tie it up nicely in the middle. And so when you look at the two Rayleigh quotients, they're almost undistinguishable. You have the same Rayleigh quotient on both. You subtract them, you get close to zero, close to like epsilon. So that's exactly what we realize is happening on this domain on H2, and we just have to formalize it. So basically we formalize it. This is how the first eigenfunction looks like, and then we constructed a good step function to multiply the first eigenfunction with to produce the other one. So H1 is the first eigenfunction. We prove it has two maxima. They get closer to the extremities as we get closer to the boundary, and then for the domain, and then the blue one, the dotted one, it's a good test function. It's orthogonal on the first eigenfunction, and we're going to use it to estimate the two Rayleigh quotients. And by estimating it, we see that the difference can be made arbitrarily small. By the way, all of these, like the functions, the H1, and when you write things in coordinates in H2, you will get, in fact, to work with a Schrodinger operator, but it's a very simple Schrodinger operator. So that's why I mentioned in the beginning that the theory for the Dirichlet Laplacian is not that much different than the Schrodinger operator theory. Okay, so somehow I'm getting ahead of myself. So, all right, so there is no fundamental gap in HN. I was kind of, taking the wind out of the sails, but we thought, we're not looking at the right convexity, because maybe geodesic convexity, especially in HN, it's very tricky. It's not like we saw they're more. See, you look at the convex, you look at the underlying space model of HN, and you realize those convex sets in HN, they're not convex in Rn. Could you do something to select among them only the sets that they're more convex than the whole set, the whole space of them? And then we realize, what is special about Rn? Rn has different definitions of convexities that are equivalent to each other. Like there is the one with any two pointer connected by a segment, and it's included in the domain. But there is also the fact that any convex set is the intersection of half spaces that support the set. Okay, so yeah, so every time you have a convex set and you have a supporting plane or half space, the set lies on one half. So you can write the set as the intersection of half spaces. And that's fantastic. But in HN, we don't have a notion of half spaces because it's not a vector space. So we can really say something of this nature. However, Santalo found a nice way to say, well, instead of using support hyperplane, I mean, what are hyperplanes in a way? I mean, okay, so why not use, okay, so I'll cut, maybe I don't do this philosophical talk, but the idea is let's use horospheres instead of half space. Okay, so horospheres are, I think, I can still have a picture here. This is the model of the this is the hyperbolic model, the disk model, Poincare disk model. This is a horosphere because it's a ball, Euclidean ball, but tangent to the boundary of. So theoretically, is a ball of Hn or H2 whose center went through infinity to the ideal boundary. Okay, because ball in the hyperbolic model, the disk model, they look like Euclidean balls, but their center is not in the middle unless you are in the middle of the Poincare disk. Okay, so we said, okay, so the right convexity to look at is the convexity, is the space of sets in HN, such that they are intersection of horoballs. Okay, so horoballs being, and you can define this in the upper half plane model or any other model, but half space model, but it's really the same. It's just just doing isometry and it's all the same. But so what do we start with here? Okay, so we decided we have a smaller space of sets. So what? Well, let's start somewhere. So let's start with the balls. The geodesic balls, they are also horoconvex, okay? Because, okay, one nice thing is that we have this interplay between convexity and differential geometry. So another way of looking at convexity is looking through the curvature of the boundary. Geodesic convexity means zero geodesic curvature, but horoconvexity means that your boundary always has principal curvatures greater or equal 1. And I mean, strictly, in fact, it's strictly greater than 1 if you are not exactly on, but in the limit you will have 1. And so what happens is you look at the spheres. Okay, so if you look at the spheres or geodesic balls, they have principal curvatures which are cotangent of R, and those are always greater than 1. So geodesic balls in the hyperbolic, they're horoconvex. So let's start somewhere, and we realized that well, we can easily show, and I think it was known, but we had a very neat new proof that the first eigenfunction of the geodesic ball is low concave, but it really did not help much, and yet we were able to obtain some estimates. For the balls, we have that there is a lower gap, there is a lower bound on the fundamental gap, which is not d squared. So this would be like the equivalent of saying it's sinh hyperbolic of d over 2 squared. Sinh hyperbolic squared of d over 2, right? Because the radius of a ball is half of the diameter. So we thought, okay, but we did not think that this is going to extend to everything, and we'll see in a moment that for the moment we don't know. Maybe it does, maybe it doesn't, but the usual bound, the usual 1 over d squared doesn't. What was the point of d squared in the Euclidean and even on the spherical? In the Euclidean particularly, you can easily see that if you have a shape in Rn and you rescale it, you take omega and you take lambda omega, okay, the diameter changes like lambda d, and the eigenvalues change like 1 over lambda, so 1 over the lambda squared, sorry, because you have 2 derivatives of. So an easy change of variables to show you that the fundamental gap times d squared, it's independent of the scaling. So that was the whole point of d squared. But that came just from the nature of the PDE. And here, when you go to the Laplace-Beltrami operator, this change of variable doesn't give you something, because the operator is not just Laplace in the coordinates equal lambda u. It has some other terms. It's not even just a Schrodinger operator. You have some first order differential terms. So you cannot do this. So that's why we were not sure that this is the right thing, and we are still not sure, and we still don't know if this extends to all horoconvex domains. But what we know is that if we still look for the d squared, because we really just wanted the d squared thing, but for horoconvex, not for all geodesically convex. So I wanted to say something, why we don't believe that this is going to extend for the whole domains. That when you go for the balls, when you go, and for any domain, we believe, as you go close to R being 0, it's a manifold, so therefore will be like close to what happens in the Euclidean space. So that's why like for very small balls, the gap is like the Euclidean gap. So okay, so that's why we think that these different two functions will not combine, will not coexist very quietly or nicely together. So so we still looked for this R squared, for this d squared thing, and we realized that even for geodesic balls it's not true. Okay, so this is the result, that it's smaller than constant times R cubed. And so so if you move R squared to the left and you let R go to infinity, in fact we believe that this might be one of the issues, the fact that the hyperbolic has this diameters going to infinity, as opposed to the sphere where the diameter is bounded from above. So from Euclidean, Euclidean is different, but spherical is just more similar with Euclidean because you can't have this very large diameter. And okay, so this was the thing for horoconvex, and this helped this basically destroyed the whole theory for all domains, because now we have that for any domain that's horoconvex, you have that the fundamental gap is smaller than, we have this technical thing that the diameter should be larger than a constant, but the constant is not so big, and in fact could probably be made more efficient, but it really just doesn't matter in a way. We're just saying that the fundamental gap is not going to be of the form 1 over d squared for any horoconvex class of sets. But I want to go quickly over some lines of proof, because then this is the end, because it's a nice way to understand convexity in hyperbolic. We already understood convexity, geodesic convexity, with these very thin balls, very thin domain that look like a dumbbell. But now we're going to look even at horoconvex, and they have something special as well. So the proof of the last theorem that the fundamental gap of a horoconvex domain is smaller than a constant, depending on dimension divided by d cube, goes through the following steps, which are all very, very nice, very simple. First, you take a ball, geodesic ball in HN with the same lambda1 as the domain. You know that this exists because they, as I said, they span the whole positive interval. And then what is interesting about compact horoconvex domains is that the smaller radius containing the domain and the biggest radius that is contained of a ball that's contained in the domain, they're never very far apart. So what it means is that if you have a horoconvex set in the hyperbolic, like here, and that set goes, so the diameter goes to infinity, the whole set goes to be grows to be a ball. It tends to be the whole space, because the two in radius and out radius, they're close together. So you can't have something very thin that's horoconvex. They're all fat sets. They are convex, in fact, in the Euclidean sense, in the underlying mother space. And so what we did is, okay, so we use this together with, we use this bound on the diameter simply because it played nicely to give us that, okay, first of all, the little radius has to be larger than this, simply from the results on in HN for horoconvex sets. And then we have that this eigenvalue has to be larger than that quantity, because it's known that if you have a set containing the other, the eigenvalue of the larger set is smaller than the eigenvalue of the inside set, because just look at the Rayleigh quotient. You have more functions to work with. You take those functions on the inside set and extend them to 0 up to the next boundary, or you have more sets, more functions that are not 0 on that annulus. And so basically, we use now the isoperimetric type inequality to say, well, okay, we have the fundamental gap of omega smaller or equal than the fundamental gap of the ball with the same eigenvalue, first eigenvalue. And for this one, we already know that this is of the form C over R cube, and R cube is basically comparable with the diameter here. So we get that's smaller than C over D cube, and then this is how what the result was saying, right? That the fundamental gap is smaller than a constant divided by D cube. So we proved that. So there is no fundamental gap as far as we know it, or at least in the way that we wanted it in the hyperbolic, even if we modify the type of set, convexity, or we choose a more restrictive definition of convexity. Maybe that's sinh squared over the diameter over 2 might work, but we don't quite believe it. And yeah, it's we just didn't find another example, because we seem to be good at proving like they don't exist, right? And these things, they're true. So that's all I wanted to say. Thank you very much.
So at this point, do you believe they don't exist?
I'm sorry?
At this point, do you believe they don't exist, or will you still try to find one or prove they don't exist?
You know, I was trying to do something like this. I was trying to say for horoconvex domains, because they are also convex in the underlying Euclidean space, try to find some comparison between the fundamental gap of the sets, horoconvex sets in HN, relative to the fundamental gap of sets in Rn. Just with some constant, some functional constant that will really show that the fundamental gap doesn't exist in the hyperbolic, but somehow a good comparison with the fundamental gap in the Euclidean. problem is the second eigenvalue. It's hard to control a second eigenfunction. It's hard to get a good test function because you're trying to compare. So you have Rayleigh quotients that are different in hyperbolic and Euclidean, and you're trying to use the right test functions from one to the other, interplaying them that they are convex in both senses. But for the first eigenfunction, you can do some comparison. For the second eigenfunction, you fail on finding the right space to look at from which to select the good test function. So I'm not sure what to believe. It's one of the things where it's like, oh, you know, it's a very bad day, nothing works. What should I do? Maybe I'll think a little bit about hyperbolic. I mean, because it's not depressing to think that the problem has no solution, but in the same time, it's not something I will put all my eggs into because I'm not sure it's going to come up.
So you're saying that you would get more mileage if you were able to do it as opposed to prove it cannot be done.
Yes, well, yes, yeah, I think so, unfortunately, yes.
No questions?
Do you think this could work in a space of variable curvature with curvature bounds instead of the...
So that's a good question. So there are all sorts of comparisons for individual eigenvalues in terms of the curvature of the ambient space. Again, the problem is, I mean, you can use some, upper bounds and lower bounds and just do a rough lambda 2 minus lambda 1, but they don't have the same asymptotic behavior, so to speak, like it's like they don't cancel nicely the terms, so you can get a function of R and that dominant term, and then you say, okay, this is what I work with. But yeah, for sure, that is something to consider. And I mean, as I said, people already looked at it. It's not new, but.
Is it conceivable that the diameter is the wrong measure? Just because, for example, in hyperbolic planes, say triangles, they're finite area, but infinite diameter and so on. So I was just wondering if this is the, some sort of 2 volume or 3 volumes or whatever.
Yeah, so we kind of all the time took the insight from the Euclidean and the spherical, but yeah, that's another thing to consider because it's probably the diameter is not comparable with the volume or something in hyperbolic. It's not the same. For sure, that's one thing. Yeah, it's hard to know, but probably once somebody figures out the right notion or the right to work with, then maybe all things flow.
I have a question. So it's related to your talk, but it's strictly related to your talk. So I seem to remember, but I've forgotten now. There are results about the filament. Results about the a bit like the flavor about the distribution of prime numbers, so the density and whatever. So could you just tell us a bit about this?
Okay,
so it's a bit different, but
so
it's more qualitative.
Yeah, so I actually don't know a lot about it, like it's not my area of research, but there are only specific domains for which you have like the whole distribution for like the asymptotic distribution. Again, otherwise you have some you can have some estimates about consecutive.
Sure. Just a kind of qualitative result about this.
That's right. But we didn't look at it. I mean, I can't say like this is the result saying how they are. I don't have something like this. I mean, and not even like I'm even talking about the Euclidean space. I don't have something that's descriptive for all domains. The other thing is that when you start to go to the higher eigenvalues, you have multiplicity as well. So it's one of the things that I'm not even sure is known how they repeat and when they repeat.
Let's thank the speaker again.
Aswa, and I want to thank Dana, and I want to thank all the speakers for putting the day together.
And Alexa,
the organizer,
and the CRM.
And Alexandra, of course.
Yes. And Alexandra, yes, Alexandra, I'm sorry.
And like that.
Merci beaucoup. Aussi le public venu. Merci pour tout ce que vous avez dit. C'était vraiment important.
Merci, Dana. Merci.